Alright guys, so I noticed that Newton, several of you have emailed me that they are using imaginary numbers in part of the problems. Um, I'm using a current textbook that's tied up with this, so in that section that we covered for quadratic functions and using the quadratic formula, it did not show any imaginary numbers. So I just wanted to give you a quick little explanation of what that is. It's not too crazy. So normally when we take the square root of a negative number, we've been saying it's undefined as a real number. So for example, when we're trying to figure out if we assume, let's say, the square root of -1 equals a real number x, then it would have to be true that when that variable is squared, you should get -1. Because when you take the square root of a number and it equals a particular number, let's say x, then x times x should equal that value inside the square root. But we know that when you multiply a real number with a real number, it has to be a positive. So that's why we've been saying it's undefined. So because there's no such real number that has that property that we have here, whenever we encounter an equation like this one, if there's a number that, if this equaled -1, then -1 plus 1 would equal 0. But because there is no such number, such real number that when you square it gives you -1, that's why we've been saying that this has no real solution. So that means we've been, at this point we're a little stumped because we've been saying there's no real solution. So let me go back into its graph and tie it in with that as well. So notice that if we look at this as a transformation, we have the parent function of the parabola, and it's shifting the y values up by 1. So we also see here that the parabola itself never crosses the x-axis, so it also doesn't have any x-intercepts. And since it has no x-intercepts, we would say that f has no real number zeros, right? Because there's no x values that we would plug in so that this function becomes 0. Exactly because we've been saying that it has no real solutions. So let me go back into history a little bit, and before I explain what imaginary number is and why we use it, let me go back in time. So a long time ago, people were just using positives and negative numbers, like 5 or -7, and they were all whole numbers, but they were either positive, 0, or negative. So when someone encountered an equation like this, and they were saying, what number can I double so that I get 3, people were stumped because there was no whole number that was a positive or a negative that you can double that would give you a whole number 3. And similarly, people were trying to figure out what number can multiply with itself so that I get a 2. We know that when a number multiplies with itself, it is going to be positive, but what kind of whole number should we put here? Just what kind of number can we think of that when you square it should give you a 2? So again, back then people would say that these had no solutions. So for this first one, they would say it has no integer solution. There's no number that's positive or negative or 0 that would satisfy, and that was it. They would stop. And for this one, they would say it has no rational solution, meaning there was no fraction that they can plug in that would satisfy that. So for this first equation here, they had to create a list of numbers that expanded what they currently knew between positives and negatives, and them being just whole numbers. So they created and they defined numbers called rational numbers. So they said, everything that we've been using, like a whole number 5, we'll just write it over 1. And all other numbers, we're going to write them as an integer over another integer. So 7 over 3 and -5/2. And that also helped them understand distance, right? You can't have a total distance of 1 inch and just 2 inches. You also have to have decimal inches. So they also used rational numbers to help them understand when something was not just a unit or a whole number away. So they created a list of rational numbers, and by creating a list of rational numbers, they were going to be able to finally answer this question. Now for the other one, once they did create rational numbers, then they were also stumped because they're like, okay, well, we expanded our list to rational numbers, but now I can't think of any fraction that I can square that would give me the number 2. So again, they were stumped and they would say, oh, there was no rational solution. So they created and they expanded their list and they find something called irrational numbers, and that's where we got numbers like pi and the square root of 7 and this number called e that is used a lot in business, or when things are growing exponentially. And that was, they were able to use that expanded list now to now have a solution for this one. So now that they expanded, let's say this one, when they expanded their list to fractions, now they were able to say, oh, okay, it makes sense for me to divide 3 by 2, because that would just give me the fraction 3/2. So then they would say, okay, the answer is going to be the rational number 3/2, because now they expanded their list so that this can answer this question. And it also had more visual meaning in terms of 3/2, right? Like where you can locate it in a ruler using decimals. And then once they expanded the list to irrational numbers, now they said, okay, it makes sense for us to take the square root of 2. It's just going to be the irrational number square root of 2, which is this very weird decimal, which is again could also be placed on a number line somewhere to represent distance. And since positive square root of 2 times positive square root of 2 will give you positive square root of 4 inside, that means that when you square it, you can get 2. And when you multiply negative square root of 2 with negative square root of 2, it becomes a positive, so it'll be positive square root of 4, and the square root of 4 is again 2, so that again satisfied this equation. So now that we expanded our list, now we didn't have to say that there was no solution. Now we knew there was a solution. It was just a different type of number from what society was accepting to be the complete list of numbers. So the same holds true for these types of equations. Majority of the people that we know, the usual folks, we just know the real numbers, the ones that our calculator, the ones that our calculators have been showing us. So what we did is we expanded our list of real numbers to create something called an imaginary number. And what we did is it was kind of based off this simple equation, and we said, I want this to have a solution. So we're going to create this thing called an imaginary number, and we're going to label it as I, just like, if I go back, just like we created the symbol square root, which back then to those people was probably a very weird symbol. And then we created something called a fraction, which was like a number over a number, which back then to those folks was also probably very weird. So to us now, we have this new symbol, I, which is equal to the square root of -1. And that's what we're calling an imaginary number. So it expands our list of the numbers that we usually know, that we deal with in our daily lives. And by doing that, we were now able to say, okay, if I equals the square root of -1, then by the properties of square roots, when I square it, I should get what's inside of it. So when I square it, I should get -1. So then we used this new imaginary number, and then we said, okay, let me do what I usually do and get x squared by itself. So I'll subtract 1 to both sides. And then I'm going to do what I would normally do for an irrational and square root both sides. And now when I do that, I get the square root of 1. So by definition, that's I. But it also turns out that you can do the other solution to be -I. And that's because when you multiply I with I, you get I squared, which by definition is going to give you -1. And when you multiply a -I with a -I, it becomes a positive I squared, which by definition also equals -1. So the number that you would need to satisfy this equation is not a real number, but it's an imaginary number. So then we use this imaginary number to then be able to have solutions for all types of quadratic functions. So like the ones you'll see on your homework look like this. And then you're going to be using the quadratic formula. So you find your A, your B, and your C. And you say, okay, I'm going to use my quadratic formula. I'm going to plug in my coefficients here. And then you work out what's inside the square root. and then you realize, uh-oh, I have a negative 7 inside my square root. But that's where imaginary numbers come in. So from here, we've been saying in class that this has no real solution because there's no real number that will satisfy this. So we would stop, and that means that that's telling us that there's no x-intercepts for this, for the graph of this function, because there's no real number, there's no real zeros where it's going to cross the x-axis. But this expanded list that we created with imaginary numbers says that, okay, we don't have a real number solution, but we do have a different type of solution using imaginary numbers. And then we use similar properties for square roots. We say the square root of negative 7, I can rewrite it as the square root of negative 1 times positive 7, and then I can split the square roots up and say, well, that's just the square root of negative 1 times the square root of 7, but then by definition, the square root of negative 1 is I. So that means that anytime you have a square root of a negative number, you can split it up into negative 1 times the positive part of the number, and then the square root of the negative 1 will pop out the I. And that's why we've been writing this as I square root of 7. So then now I can rewrite this as I square root of 7, and then I can continue with my mathematical properties here. Notice that when you have two things adding or subtracting over the same denominator, they can be split up each into the same denominator. So then I can rewrite this as a solution where I'm going to have negative 5 halves plus or minus the imaginary number I root 7 over 2. So in your homework, when you guys end up with a negative square root for that quadratic formula section, just know that you're not going to have a real number solution. When you have a number with an imaginary number, your textbook is going to call these complex numbers. Okay, that's as deep as it'll go. I'm not going to go any further in the class with this. And that was my mistake. I really believed that Newton wasn't going to show any of these, but I guess it did. So I just wanted to clarify that for you. Have a great weekend.